Hello, everyone, and welcome back. In this lecture, we are going to discuss indefinite integrals. And this is going to be a direct extension of everything that we discussed in the previous lecture, where we presented the fundamental theorem of calculus. And what we saw with the fundamental theorem of calculus is that it helps us interpret integration as a sort of undoing or a backwards operation or an anti-differentiation from the derivative operator. And so we're going to take this a little bit further today, and we're going to talk about what it means for something to be an antiderivative and how we can find them. And in particular, the method that we'll use is what's called the substitution method for these indefinite integrals, which, as you'll see, is essentially undoing the chain rule. So if you think of the chain rule for derivatives, the substitution method is undoing it. It's moving back up into the antiderivative realm. So let's go ahead and get started. What we saw with the proof of the second part of the fundamental theorem of calculus is that there are infinitely many antiderivatives associated to any continuous function. We should put that qualifier in there. And what we further saw from the differentiable mean value theorem, we discussed that all of these antiderivatives are just a constant away from each other. So that means that if you have one antiderivative, you can add any constant to it and get another antiderivative. This is very interesting because this tells us that there's infinitely many antiderivatives for any function, right? One for every single possible constant that you can add on the end. So what we do is we introduce a shorthand to denote the set of all possible antiderivatives of a function f of x. And it looks a lot like our usual integration notation. We just use this notation right here to denote the antiderivatives of f. Now, the only difference between this and a definite integral is that we don't have any bounds on the integration. And so this actually gives us a function where f prime of x is equal to f of x. So this gives us all possible antiderivatives. This is just a shorthand notation for describing these functions. In the same way that when we had the definite integral like this was just a shorthand to represent all possible, the limit of these Riemann sums. And there's not a coincidence that we use these two notations. In fact, they're directly related to each other. And let me show you how. So first of all, from the fundamental theorem of calculus, we know that this is equal to f of b minus f of a. Adding and subtracting c to both to the right-hand side gives us that we can write this like this. We're basically undoing the proof of the second part of the fundamental theorem of calculus here. And this f of b plus c and this f of a plus c, this is the same using this shorthand notation that we introduced in the last lecture, which is really just this antiderivative notation like this. So you can see this relationship between these two things, right? One of them is giving you the antiderivative. That's the first one without any bounds. But when you start evaluating this antiderivative, then what you get is you just are essentially putting on the bounds for this definite integral. And again, this is just a consequence of the fundamental theorem of calculus. And the one thing that I really, really, really want to emphasize to everybody here is that this term right here is a function. This is a function of x. This term right here is just a number. Remember, that's our sort of abstract notion of area right there. So there is a difference between these two things, right? But from the fundamental theorem of calculus, they are directly related to each other. Okay, so with this intuition, we can start asking ourselves, how do we find antiderivatives? Because clearly the fundamental theorem of calculus tells us that if we want to evaluate definite integrals, we really need these antiderivatives. So what are some techniques and some tools that we can use to actually find antiderivatives? If I give you a function, how do I find its antiderivative? Well, we are going to talk about the method of substitution here. And this is, as I mentioned at the top of the video, this is essentially running the chain rule backwards. So what do I mean by that? Okay, let's assume we're given a function u of x that is differentiable. And let's take some number n, which we're not going to choose to be, it can be anything but -1. Okay, well then the chain rule gives that if I want to take the derivative of u raised to the power of n, so u to the power of n, I'm going to, u to the power of n plus 1, I'm going to divide by n plus 1 just so that the derivative looks prettier, right? Because we remember taking the derivative of polynomials, the exponent comes down. So when that exponent comes down, it'll just cancel off with the over n plus 1 on the bottom. That's the only reason I'm writing it like this. I think it's just slightly more compact. But what this gives me is that this is equal to u to the power of n. I decrease the exponent, I evaluate at the inner function u, and then I multiply this by the derivative of u. Okay, so then I can take an alternative point of view of this thing. And I can also say that this function, u to the n plus 1 divided by n plus 1, is an antiderivative of un times du dx, right? That's exactly the same statement, right? If I take the derivative of u to the n plus 1 divided by n plus 1, and I get the right-hand side there, then clearly that's the antiderivative. And then now I can use my fancy new indefinite integral notation. And this says that u to the n times du dx, that's a function on the inside, multiplied by dx, is equal to u to the n plus 1 divided by n plus 1 plus c. We're going to forget it. I know we're going to forget it, but please do not forget the plus c, right? There are infinitely many antiderivatives in that are equally valid. I could choose c equal to 1. I could choose c equal to 0. I could choose c equal to 1,000,000 to the power of pi. Still a valid antiderivative. So we need to make sure that that c is in there. But let's just look at this for a moment. And let's sort of think about what's happening here. Especially what I want to focus on is this right-hand side. So maybe you've taken another calculus class before, and maybe your professor has sort of remarked to you, or maybe stronger than that, maybe they sort of impressed or yelled at you that you should never think of du dx as a fraction, right? These are infinitesimals. This is a change in u by the change in x. We should never really think of these as fractions. I agree. I certainly agree with that. But there is something kind of nice going on here, right? If I can informally cancel out those dx's, we get something that we already knew, right? And this tells us, if we were just integrating with respect to u here, instead of with respect to x, we would get the same answer. Right? So this suggests that we can do a little bit of substitution in here. We can view this integral in two different ways. we can think of this integral as being this polynomial integral at the bottom here, which is relatively probably easier, as we're going to see with the examples here, because I can find antiderivatives of polynomials all day. I think that's a fairly straightforward task. Whereas, u might be a very, very complex function, and its derivative showing up in the second to last integral here could be very, very complex. Now, another way to justify this is we can think of this relation right here, because essentially we're saying the following: du is equal to du dx times dx, right? That was the substitution that I just made in the previous line. So what does this say? Okay, if we go all the way back to Riemann sums, and we sort of intuit these things. Remember, these du's and these dx's, these are limits of delta x and delta u going to 0. And what is delta x? It's nothing more than just a change, right? It's a change in the x variable. So what does this tell us? This tells us that the change in the u variable is the same as finding the change in u with respect to x, and then finding the change in x, right? So this is an implicit dependence. This is exactly what comes through when you're doing the chain rule. And so maybe you're thinking to yourself, okay, Jason, that's fine. Maybe I'm following you, but I don't really see how this is going to help me, right? I get it. It's just abstract math. So let me give you an example. Let me show you this in practice and how we can use this properly. So let's say example 1. So let's find the antiderivative, all possible antiderivatives, the indefinite integral of x cubed plus x to the power of 5 times 3x squared plus 1 dx. Okay, so that's a pretty hairy function, right? It's not pretty, it's quite ugly. And just on the surface, I'm not really sure what the antiderivative is. I suppose if I really wanted to, I could expand this with the binomial theorem, and I could get this massive 17 degree polynomial. But I'm going to tell you, you don't have to do that. You should see this as a chain rule. And so how are we going to do it? Well, we're going to set u is equal to x cubed plus x. Okay, so that means that this first term in the integral is actually u to the power of 5. So I'm going to sort of compactify this. I'm going to say that whole thing is u. Okay, then from what I have above, this tells me that the infinitesimal change in u, du, is the same as the derivative of u with respect to x times the infinitesimal change in x. Okay, not bad. Du by dx is a polynomial. I can do this. So I've got 3x squared plus 1 times dx. Oh, that's interesting though, right? Because look what happened. In my integral, the whole first term became u to the power of 5, and the whole second term, 3x squared plus 1 dx, is going to be replaced with du. So let me just run back to what we saw in the previous piece here. I was given this line right here, and it was complicated and it was ugly. It was u to the power of something. In my case, n was equal to 5. And then the derivative of u was actually hanging out on the back there. And with that substitution, I'm allowed to move to a much simpler integral, right? So let's go back and let's take a look at this. Oh, sorry. So now, what does my integral become? Well, my integral was x cubed plus x to the power of 5, 3x squared plus 1 dx. Now, with my substitution that I did, I have u to the power of 5, And maybe we should emphasize this. This is equal to u to the 5. This is equal to du. And so now I have an integral of a polynomial function in u, right? The independent variable is now u. I compactified everything. And so this is a nice, easy integral for me to do, or the antiderivative of this thing. I just increase the exponent by 1, divide by that new exponent, and I add c. But just like what we did in the previous lecture, nobody asked me about u ever, right? The original question was asking me about x, so I've got to put everything back in terms of x. And so that means that I need to have x or u replaced by the function of x, which was x to the 3 plus x to the 6 divided by 6 plus c. Do not forget the plus c. Okay, so easy, right? Life is good. I can do this all day. Let's scale up the complexity though a little bit. Okay, so let me give you another example. Let's think about this. So example 2. Okay, so let's find all antiderivatives of the square root of 2x plus 1 dx. Okay, the first thing that I'm going to do is I'm actually going to write that square root as an exponent, just so we can see this. This, in fact, does fit into the framework that we just talked about. So in this case, n is equal to 1/2. It's perfectly valid. So it seems to me that I want to substitute u is equal to 2x plus 1. I'm going to follow what I just did. So let's try it. Let's try it out. So let's set u is equal to 2x plus 1. Okay, then, so du, du is equal to du by dx times dx. Now the derivative of u with respect to x, that's 2. Okay, so we've sort of hit a wall, right? Because now I only have one dx in my integrand. I do not have 2 of them. So what am I going to do, right? Am I completely messed up? Is there no way to resolve this? Well, no. Luckily, we can use some of the properties of integrals. We can add in, or we can multiply and divide by 2 in this thing, and we can artificially put that 2 back in there. So let me show you what we're going to do. So this integral of 2x plus 1 dx, I'm going to multiply and divide by 2, just so that I can put the 2 dx in there. So I get the integral of the square root of 2x plus 1 times 2. Let me put the 1/2 first. Times 1/2. And then times 2 dx. Okay, this is good, right? Because now I've got u under the square root. I've got a du here. And if we remember some of the properties from definite integrals, the same properties carry over to indefinite integrals. So that 1/2 can be pulled outside. So let's do all this in one nice clean step. I get 1/2 the integral of u to the power of 1/2 du. And now, again, this is just a sort of, I know it's not a polynomial, but it looks like a polynomial because it's just u to the power of an exponent. So life is good again. So what do? I add 1 to the exponent, 3/2. I divide by the new exponent, and I add c. Okay, and again, keep in mind, nobody asked me about u. U is something I put in, I made it up. People asked me about x, right? That was the original question, that this was the original variable this was posed in terms of. So I gotta resubstitute u back in for x. So now I can simplify all of these numbers out front. I get 1/3 And substituting back in for u, I get 2x plus 1 to the 3 over 2 plus c. So we've got a nice antiderivative of the function of the square root of 2x plus 1. So this is pretty cool, right? We're sort of undoing the chain rule. I know that typically when we learn the chain rule, it's very difficult, right? We have a lot of trouble with it. A lot of people make mistakes with it, including myself. But somehow, to me, this feels slightly simpler. There's something about it. It feels easier than doing the chain rule. Maybe I'm wrong, and let me know if you think that I'm wrong about this. But I am under this belief. Okay, so let me summarize something here for you. This doesn't, I don't always have to just wind up at a polynomial to integrate, right? This is going to work for any function. So let me introduce to you what's called the substitution rule. The substitution rule is exactly undoing the chain rule. So if I take the integrand of a chain rule, so sorry, f times this dx. So if the derivative of the function is hanging out back of this thing, then I can simply introduce u is equal to g of x and see that this is the same as integrating this by u is equal to g of x, right? So it's exactly the same principles. We've just been using f is just a single exponent function, right? So f of u is equal to u to the power of n. But this works for any general f. And so let me give you an example, right? Let's put this into practice with something that's slightly more complicated. So example number 3. Let's find the antiderivative of secant squared 5x plus 1 times 5 dx. Okay, so hopefully you're getting an eye for this a little bit. So you're probably able to anticipate what I'm going to substitute for. And this is certainly, as you start doing more examples, this will be the case. So I'm going to let u equal to 5x plus 1. And this tells me I'm going to skip a little bit of steps. Remember that du is equal to the derivative of u with respect to x times dx. So this is 5 dx. And so that integral that I was given, secant squared of 5x plus 1 times 5 dx. Again, if I want to make a note on here, this thing is equal to du. This thing is equal to u. And so I just get the integral of secant squared of u du. So in this case, if you use my substitution rule up here, g is equal to my u function, 5x plus 1. F is equal to secant squared. And so this one, you might have to reach deep into the recesses of your mind to remember what the antiderivative of secant squared is. I'll ruin the surprise a little bit. It's tan. So we get tan of u plus c. Never forget it. And again, nobody asked me about a u. They asked me about an x. So I've got tan of 5x plus 1 plus c. That is beautiful, right? It's just a work of art. Let's just keep going. We're gonna hammer on a ton of examples here just so that we can drive all of the points and nuances of this home. Let me give you another fun one. Trig functions are the best functions on the planet. So let's keep playing with trig functions. Cos of 7 theta plus 3 d theta. So I'm integrating with respect to theta. And let's take a look at what I can do here. Well, again, you're probably getting good at anticipating this. So I'm going to let u equal to 7 theta plus 3. And then this tells me that du is equal to du by d theta times d theta, right? So don't be intimidated by the fact that I moved from an x to a theta. It's all just a variable. Remember what I said in the last lecture. You can make up your own symbols for these things for all I care, right? You can use Greek letters. You can use the Latin alphabet. You can use the Cyrillic alphabet, whatever it is that you want to use. We just have some standards in mathematics like x's and thetas. Okay, so what do we have here? We have 7d theta. Okay, so now we have a problem, right? It's the same problem that we had with the second example. We don't have that 7 floating through, but no fear, right? We know how to do it. We can multiply and divide by 7, and we can easily do this substitution. Let me show you a little shortcut though, right? We don't have to do that multiply and divide by 7 every single time. I can just rearrange this formula right here. I can actually isolate for d theta because that's all that I have. And I can say that d theta is equal to 1 over 7 du. This has the same effect as multiplying and dividing by 7, right? Go back to that second example and see for yourself. And so if I do this integral, the 1 over 7, it's going to come out in the same way it did with the second example. So let me take it out right off the bat. I get the integral of cosine of u du. And now I look for the antiderivative of cosine. Well, in that case, it's just sine. So I get 1 over 7 sine of u plus c. And then finally, nobody asked me about u. They asked me about x, or they asked me about theta in this case. Let me put it all in terms of theta. So I get sine of 7 theta plus 3. And then never forget the plus c on the end. So this is fun, right? It's exciting. It's exhilarating, right? It's we have this way to find antiderivatives of functions that look relatively complicated. And this is a way of generating new functions from functions that we already knew, right? So let's keep it going. We're just gonna drill examples for the remainder of this. So let me give you another one. The integral of x squared e to the x cubed dx. So that is a horrible function, right? It's pretty ugly. But let's take a look at something, right? So this is the typical difficulty that comes in with substitution, right? What should I substitute for? And you want to substitute for as much as possible so that you can make that integral as simple as humanly possible. So maybe, let me illustrate this by example. This is going to be wrong, so don't write this down in your notes, but let me show you what can happen here. Maybe you want to try and get rid of that entire exponential term, right? You can say let u equal to e to the x cubed, right? So maybe you're getting a little ambitious. You're thinking, I could probably get rid of that whole thing. Well, what happens here? I get du is equal to, now the derivative of that function right there, that's going to be 3x squared e to the x cubed dx. Okay, so think about what happened here. This isn't bad per se, because look what happened. This term becomes a u. The x squared and the dx, that's okay because they're right there. But the question is, what do I do with that? Right? Another u showed up. I don't really want that, right? That's way too complicated, right? Things didn't quite close the way that they should have. And you could you could still work with this if you're sitting behind the screen and thinking about this. Yeah, you can make this work, but it's going to be way more complicated than it needs to be. So let me show you how you can tone this one down without being so ambitious. What you can see here is that there's a polynomial at the top of this, or in the exponent, and its degree is 1 higher than this polynomial floating outside. Now, what do we know about polynomials? When you take a derivative, you lose 1 order. The degree goes down by 1. So that means that if I substitute for x cubed, then the du term is going to give me an x squared in it. So let's try that. Let u is equal to x cubed. This tells me that du is equal to 3x squared dx. This isn't bad, right? I have an x squared, I have a dx. The 3, we know how to deal with this. I can just rearrange this. I can say 1/3 du is equal to x squared dx. And so everybody is accounted for. Everybody's taken care of. Because I've got e to the x cubed dx. And now I get the 1/3 coming from the du term. And I've got e, so maybe I should write this underneath. This is equal to e to the power of u. I will say this and this is equal to 1/3 du. And so everything together, e to the u du. Now I'm left with an exponential function to find an antiderivative of. And the beauty of exponential functions are that they differentiate into themselves. And so that tells me that the antiderivative is again itself plus c. And then finally, put everything back in terms of x. So I get 1/3 e to the x cubed plus c. Okay. So great, right? Things are easy. Let me show you another example. So in the one that I just showed you from example 5, you actually could have made it work the way that I did it originally with the exponential. And the next example is going to show you how to do that. So in some cases, not everything disappears the way you want it to, but things can still be recovered. So let's say evaluate the indefinite integral x square root of 2x plus 1 dx. Okay, so conventional wisdom here that we've gotten over the past, 20 minutes, is telling us that we should be substituting for 2x plus 1. That's probably what we want to do. So let's try it out. Let's work it through. Let's see what happens. So let's let u equal to 2x plus 1, which tells me that du is equal to 2 dx. And so this tells me if I divide off by 2, I get 1/2 du is equal to dx. Okay, not too bad. So putting this all together, this will tell me that this term on the end of the integral, this just gets transformed into this, which is something I can manage. But that's not the whole integral, right? There is still this x floating outside. And so the question is, what do I do with that, right? It wouldn't make sense for me to pose this in terms of x's and u's. The whole point was to get rid of the x's. So how can I get rid of it? Well, it can be kind of clever, right? So since u is equal to 2x plus 1, I can rearrange this. This function's invertible. And this tells me that x is equal to 1/2 of u minus 1. So I can solve for x as a function of u. And what this tells me is that now, when I take my original integral, I accounted for this piece right here, and I said that it's 1/2 the square root of u du. And now the x term right here is equal to 1/2 of u minus 1. And now if you see what happened, all the x's are gone, and all I'm left with is with u terms. So let's actually do this. This gives me 1/4. I get a 1/2 coming from the x substitution, a 1/2 coming from the du substitution. And I get the integral of u minus 1, u to the 1/2, that's the square root of u, du. Not bad at all, right? So now I can expand this out. This leaves me with 1/4 u to the 3/2 minus u to the 1/2 du. Now I'm running out of room on this page, so I'm going to flip over. But before I do, let's take a look at this. These are fairly easy things to integrate, right? We know that taking derivatives is linear. So that means that antiderivatives is also linear. It means I can evaluate the antiderivative of each one of these terms and then just subtract them to find the final answer. So let's keep going here. And this gives me 1/4. And then integrating up that u to the 3/2, this is going to give me 2/5 u to the 5/2, and then minus 2/3 u to the 3/2. That should be squared just to be consistent. And then plus c, right? And so if you're wondering where the 2/5 and the 2/3 came from, it's the dividing by n plus 1 term, right? So I'm dividing by 5/2. When you divide by it, you invert and multiply. And so now let's clean it up a little bit. This gives me 1/10. That's 1/4 times 2/5. Substitute back for x. So I get 2x plus 1 to the 5/2. Same thing, 1/6 here now. 2x plus 1 to 3/2, and then plus c. So that's my antiderivative of that function. This is great, right? But now we have a lot of interesting tools at our disposal and ways for evaluating and finding these antiderivatives that can help us use the fundamental theorem of calculus, right? So don't lose sight, right? We started with approximating areas and then moving to the Riemann sum and then converging it to give us a definite integral, then using the fundamental theorem of calculus to find actual answers to the definite integral in terms of antiderivatives. So we're a little down the rabbit hole now, but the whole purpose is to go all the way back to find, for example, these areas or maybe these displacements or these averages that we talk about. Okay, let me keep going then. So example 7. I love trigonometric functions. I think I've already said that in this lecture. So let's keep it going. Let's play with the trig function. Sine squared x dx. Okay, this one's not great, right? It doesn't really seem to be anything to substitute for, right? It's not sine squared of some function of x. It's just sine squared of x. If I substitute for x, I just get u is equal to x, I get du. It's not helpful. What the heck do I do here? Well, trigonometric functions come with all kinds of trigonometric identities, right? So what we're going to use is we're going to use a nice trigonometric identity, which tells us that sine squared is actually equal to 1 minus cos of 2x divided by 2. Okay, so let's see if this helps us. I'm going to pull the divided by 2 out front just to make it look a little cleaner in presentation. 1 minus cos of 2x dx. And so now what I have is something that I can actually solve for, right? If I want to, I can do a substitution for u is equal to 2x here. And that's going to clean everything up for me. I'm going to go ahead and skip the steps. I'm going to leave it for you to do the substitution as an exercise, but I will give you the answer. You get 1/2 x, that's from integrating up the 1 term here, minus 1/2, and then integrating up, finding the antiderivative of cos of 2x, that's sine of 2x, so that will be your sine of u term, divided by 2, because you're essentially, the divided by 2 comes from the substitution with dx is equal to 1/2 du, and then plus c. So if you want to clean it up one more, you get minus 1/4 sine of 2x plus c. So it's pretty. And so I'm not going to do it in this video. I'm going to leave it for you. Try this one out. Try and find the antiderivative of this thing using trigonometric identities. So you might have to look up some trigonometric identities. I'll give you a hint. It's a double angle formula, but try it out. And you can do the same thing by finding the integral of tan of x by using this formula. We know tan is sine over cos. So try substituting for cosine in this case. Again, I'm going to leave it as an exercise because I think it's a little more rewarding if you do it than if I do it. Okay, so let me do one last example here, and I want to show you things can get pretty complex pretty fast, and we might have to do a little bit more manipulations than just a trigonometric identity to simplify these things. So here's what I'm going to give you. I want to find the antiderivative of 1 over e to the x plus e to the minus x. Again, this isn't going to be too simple right off the bat. If you try and do some substitutions like e to the x, this e to the minus x is going to be a pain. If you substitute e to the minus x, the e to the x will be a pain. So here, I'm going to use a clever little technique. E to the minus x is the same as 1 over e to the x. So let me multiply the top and bottom of this fraction by e to the x, right? So multiplying top and bottom of a fraction by the same number or same function is not going to change anything. So, but let's see what happens. This gives me the integral of e to the x. Now, on the bottom, I have e to the 2x. This is e to the x and then all squared, right? This is how these exponents work. And then plus 1. Great. Okay, so did this help me? I'd like to think so. So let me propose something. Let's say let u equal to e to the x. And so clearly du is equal to e to the x dx. Okay, so did that help me at all? Well, I do have an e to the x dx at the top of this fraction. But the question is, well, how does the e to the 2x work? Well, e to the 2x is the same as e to the x squared, which is the same as u squared. So that tells me that this thing becomes du over u squared plus 1. Now, we just need to know what is the antiderivative of 1 over u squared plus 1. This one, we might have to dig deep back into our mind for this, but I'll ruin the surprise. This one is the arctangent, so the inverse of the tangent. So arctan of u plus c which is the same as arctan of e to the x plus c. Great, right? That actually wasn't that bad. It was only what, 4 equal signs, four manipulations. That wasn't bad at all. Okay, so now we have a new tool at our disposal, and we have a new way of finding antiderivatives, and that's the method of substitution. And again, keep in mind this duality between integration and differentiation that comes from the fundamental theorem of calculus, right? These are inverses of each other. They are undoing what the other one is trying to do. And so with all of the methods of integration that we're going to learn, they are undoing the methods of differentiation that we've already learned. So this method of substitution is really just undoing the chain rule that we learned when we talked about derivatives. Okay, thank you very much.